This is Learning Assessment Problem 916. The problem-solving strategy here is that of complex power calculations. The problem states that an industrial load requires 40 kilowatts at a 0.84 power factor lagging. The load voltage is 220 volts at an angle of 0 degrees. The frequency is 60 hertz, and there is an impedance associated with the series transmission line. And we are to determine the real and reactive power losses in the line and the real and reactive power which must be supplied at the input to the transmission line. With the 0.84 power factor, we can calculate the phase angle at the load. This would be the angle difference between the voltage and the current in the load. This is equal to the inverse cosine of that 0.84 power factor, or theta sub L, is equal to 32.86 degrees. Now we can calculate the magnitude of the complex power at the load. That would be S sub L magnitude is equal to the power dissipated in the load divided by the cosine of that phase angle, theta sub L. And that is equal to 47,619 volt amperes. So that's the magnitude of the complex power term. Now we can calculate the reactive or quadrature power at the load as S sub L magnitude times the sine of that phase angle, theta sub L. And that quadrature power at the load is equal to 25,837 volt amperes reactive. Now we can write the complex power in its complex form is equal to P sub L plus JQ sub L, and that is equal to, or S sub L is equal to 47,619 at an angle of 32.86 degrees volt amperes. Now we have the relationship between the complex power S sub L at the load and the voltage and current at the load. And that is equal to V sub L phasor times the complex conjugate of the current phasor I sub L. Then we can solve for the current I sub L is equal to S sub L divided by V sub L phasor and the complex conjugate of that quotient, or the current is equal to 216.5 at an angle of minus 32.86 degrees amperes. Now we can use this current information to calculate the power associated with losses in the transmission line. The power dissipated in the line is equal to the magnitude of the line current phasor squared times the resistance associated with the transmission line, or P line is equal to 4.685 kilowatts. Similarly, the reactive power loss in the line is equal to the square of that line current magnitude times the reactance of the line, and Q sub line is equal to 11.713 kilovars. The power supplied by the source is equal to the power dissipated in the line and the power consumed by the load, or P source is equal to 44.685 kilowatts. Similarly, the quadrature power supplied by the source will equal the quadrature power consumed in the line impedance plus the quadrature power associated with the load, or the quadrature power supplied by the source is 37.75 kilovars.